Hello everyone, this is Suraj Kothari. Welcome to the segment 4 of my talk. So last time we talked about the algebraic method. We discussed how to get the compact representation for execution behaviors by setting up a linear system of equations with successor elements as the coefficients. And then by solving the linear system of equations, we get a compact representation, CRS, and we map CRS to CRB, the compact representation for behaviors. Towards the end, we discussed program with a loop. So this is the program. We have statements A1, A2, A3, A4, A5, and we have a loop A2, A3, A4, A5. Setting up the equations and solving the equation works as before. We treat E2, E3, E4, E5, the successor elements, as numbers, and we can do the division 1 divided by 1 minus E2, E3, E4, E5 and get this solution. The problem is, how do we interpret it as execution behavior? Recall that the successor elements are pairs of program statement. So E2 is A2, A3, and we map the successor element E2 to A2. But when the successor element is in the denominator, the program statement appears in the denominator. And so how do we make sense of a division where the program statement is in the denominator? How do we get a sequence of program statements? So this is something that became a major roadblock as I was working on this algebra. How do we make sense out of division? So let's recall that the multiplication AB is behavior A followed by behavior B. Addition A plus B is union behavior A or behavior B. The additive identity is an empty set of behaviors. To define division, we need multiplicative identity. We denote it by 1. Multiplication by 1 is no change. 1 corresponds to the null behavior. But the question is, when we have 1 divided by 1 minus A, where A is some algebraic expression involving the successor elements, what behavior would it be? That's the division puzzle. As I was working on it, I remembered Dirac. I had gone to attend a lecture by Dirac. It was 1979, Einstein's birth centenary. The front 3 rows in the room were reserved for Nobel laureates. As Dirac entered, the Nobel laureates stood up in reverence. As I watched them, my elementary school days flashed before me. Their reverence was like the reverence with which we used to stand up when our teacher entered classroom. After Dirac gave the lecture, someone asked a question. Sir, what made you think of antimatter? Dirac responded, what do you mean, what made me think of antimatter? An equation with real coefficients has complex conjugate roots. One root corresponds to matter. What does the conjugate root correspond to? After a pause, Dirac says antimatter. Dirac showed an unusual way to make sense out of conjugate root to relate it to matter. We need to make sense out of division to relate it to execution behaviors. The solution that I am going to present to this puzzle that we have, is a tribute to my algebraic geometry guru, Sri Ram Abhyankar, who told me, "Be brave, do not be afraid of infinite series." An infinite series comes to our rescue here. So think of the multiplication 1 minus a multiplied by the infinite series a to the power I goes from 0 to infinity. When we do the multiplication, we get 1. So 1 over 1 minus a is the infinite series a to the power I goes from 0 to infinity. This infinite series makes sense as execution behavior. So we had 1 over 1 minus e2, e3, e4, e5. That becomes the infinite series, and the infinite series can be interpreted as behavior e2, e3, e4, e5 repeated 0 or more times. We will denote repeated 0 or more times by star. So this is what we can do. So we have x1 is equal to e1 times 1 divided by 1 minus the expression with successor elements e2, e3, e4, e5. So we write that as e2, e3, e4, e5 star followed by e6. Now the CRS is here. We can easily map it to CRB the way we did it before. Each successor element gets mapped to a program statement using the rule we discussed earlier. So we get the CRB which is shown here, and this CRB makes good sense as the execution behavior for this program. So we start at A1, then we have A2, A3, A4, A5 repeated 0 or more times followed by A2 and then E. So the division can be interpreted as an iterative behavior. We have a few more examples here to illustrate how the algebra works in presence of loops. Here is an example of two non-nested loops, and we have the CRB. The CRB shows that we start at A1, then we have the loop A2, A3, then we exit at A2, then the second loop A4, A5, we exit at A4 and end with E. Here is an example of a nested loop, and again if you look at the CRB, it's pretty clear that the CRB represents all the execution behaviors. Here is an example of a 3-level nested loop. Now let's come back to the example we introduced earlier. This is an example where we want to verify that lock is always followed by unlock. This example is actually taken from the Linux kernel. We have stripped off a lot of code to focus on the key point. Here we have a loop, and the lock and unlock are inside the loop. We also have a break. Typically when we enter a loop, it has one entry and one exit, and the exit is same as the entry. But a loop can have multiple exits either because of break or a return. So in this case, the loop has one normal exit and one exit because of the break. Before we go to the CRB, the compact representation, let's introduce the idea of basis behaviors for a loop. This would make it easier to understand the solution that we get and how to think about loop behaviors. A loop either has a complete iteration as a basis behavior, or a loop may have a partial iteration when the loop stops in the middle because of a break or a return. So in this case we have a return, so we have one partial iteration. We can enter the loop. When C1 is true, we have a lock. Then we have if C2, if C2 is true, we have a break and we will exit. So that's what's shown here, that if 5 is true, then we have a partial iteration. So in this case, if we count the number of loop behaviors, if the loop iterate n times, the first n minus 1 iterations must be complete iterations. And there are two possibilities here for complete iteration. So for the first n minus 1 iterations, we have 2 to the power n minus 1 possibilities. For the last iteration, it can be either an exit with a partial iteration, or it could be simply an exit at the loop entrance itself, which we will call no iteration. So for the last iteration, there are two possibilities, either the partial iteration or no iteration. So if we have n iterations of the loop, we have 2 to the n possibilities. So even for just n equal to 50, the number of possibilities can be enormously large. The idea of basis behaviors comes from the notion of basis for vector spaces. Now let's look at the CRB for this example. You can see that we have the beginning, then statement 2, then we have a loop, and after the loop we have a partial iteration and then the end. Okay, so the last iteration is either a partial iteration or no iteration. Here we have shown the details of how we get the CRB. Again, we start with the linear equations, solve this system of equations and map the CRS to CRB, and we use the division as we have defined before by taking help of an infinite series, which leads to iteration of behaviors. And here is a mapping from CRS to CRB for this example. So let's now summarize some benefits of the algebraic approach. The algebra enables efficient algorithms for analyzing software. So for example, if we want to count the number of behaviors, we can count it readily using the CRB. So enumerating the behaviors is intractable, but counting them using the CRB is pretty efficient. The order of computation is O(n), where n is the number of program statements. Later on, we'll see other examples of efficiency due to algebra. Especially we will talk about homomorphisms to compute relevant behaviors, and we will also apply homomorphisms for analysis of software across multiple functions. Here is an example from the GNU operating system. This DSK opt is the function. In this case, the function has 46 statements, and so we have 46 variables, and we get the CRS for the function. And if we look at the CRS, looks complicated, but just by using the rules of operations like the distributivity, associativity, etc., especially the distributivity, we can count the number of behaviors. It's 10. Now let's point out the key reason for efficiency of algebraic approach. Here is a function with two loops, and we have the coefficient matrix. When we set up the equations, we have the coefficient matrix. The coefficients are the successor elements. So there are two things to observe. First of all, it's almost a diagonal matrix, and the second is the sparsity. Every row has only one non-zero element, or at most two when it is an if condition. The only entries below the main diagonal are the entries which correspond to the loops. In this case, we have two loops, and there are two entries which correspond to those two loops, E8 and E10. Later on, we'll go into more details of this coefficient matrix, but right now we want to point out the structure of the coefficient matrix enables order n operation to solve the linear system. When the program is unstructured, the example that we presented earlier, we have the CRS for that example. If we look at the coefficient matrix, although the program is unstructured, the structure of the coefficient matrix remains the same. The sparsity and the only entries below the main diagonal are the entries which correspond to the loops. So to summarize the complexity of CRS and CRB, the main thing to keep in mind is the number of successor elements is at most 2n, where n is the number of program statements. Computing the successor relation is n log n, and solving the system of equations because of the structure of the matrix is order n. This algebra can be applied to structured as well as non-structured code. It can also be applied across multiple languages. So the infrastructure that we have developed is language independent. Currently, we can handle Java, Java bytecode, C, and the binary code for some architectures. To handle a particular language, we need to have the front-end processor, and the front-end processors are currently built for some languages but not for all. The algebra is applicable within a function, or all our examples so far have been within a function. Later on, we will look at how to apply the algebra across functions. We get high accuracy because all execution behaviors are analyzed accurately. We do not use error-prone approximations, and we can do accurate reasoning of complex loops irrespective of the number of iterations. We have used this for analyzing the Linux kernel. We have found bugs in the Linux kernel which are now accepted by the Linux developers. More interestingly, we have compared our results with the results using a model checker, and we have found some errors that the model checker makes. We have few more examples of computing CRS and CRB. Here is an example with a loop and a break. Here is another example, a loop but two breaks. Here is an example of a nested loop and the break is inside the nested loop. Here is another example of a nested loop with a return. In these examples, there is one interesting thing to note. If we look at the CRS has some repetitions. So for example, in this when we have a loop with two breaks, E2 repeats twice in CRS. Now here we have an example with a break with a return in a nested loop, and we have repetitions. If E4 repeats twice, E2, E5, E7 repeats once in CRS. Without a break or a return, the earlier examples that we looked at, you will notice that we do not have any repetitions in CRS. We have summarized the repetitions. So with break or a return, we get repetitions. Without a break or a return, we do not have any repetitions. This got me thinking. At the beginning, the control structures in structured programming were not allowed to have multiple exits. The control structures were required to have unique entry and unique exit. The requirement was relaxed later, and now we can have multiple exits in a control structure because of break or return or due to exception handling. Now the question comes up, the repetitions that we get in CRS, do they have something to do with the structuredness of a program? We did some experiments and we will come back to this question in a later segment.